Welcome to another episode of the NACE International podcast. My name is Sammy Miles, and I'm the Managing Editor-in-Chief of Corrosion Journal, NACE's peer-reviewed scientific journal. Today, we're kicking off the new Corrosion Journal interview series. I'm joined by one of Corrosion Journal's associate editors and authors, Professor Nick Burbillis. He is the Deputy Dean of the College of Engineering and Computer Science at the Australian National University in Canberra. Today, Nick and I will be discussing additive manufacturing of metals and alloys. Nick, thanks for joining.
Thank you so much, Sammy, and thanks to NACE International for having me today. It's a real pleasure to have the chance to speak to you all.
Thank you again. And before we jump into today's conversation, do you want to share a few details about your background in corrosion and materials science?
Oh, I'd love to. Well, look, one of the things with materials science and how I got into it is when I decided to go to college, I had no major, and I decided to pick something that was going to be interesting. And of course, the thing with materials science is until you've had a little bit of exposure, you don't realize just how interesting it is. So if you think about some examples about, the materials on the space shuttle to allow it to re-enter and come back to Earth, or the way silicon makes our computers work, or materials that can harvest electrons, getting excited about materials was something that came naturally to me. And I guess the more you dive into materials, the more you realize they're engineered products. So humans are responsible for making them and their properties. And so then the most exciting part of materials to me is how do you keep them that way? And that's where I got really interested in corrosion in terms of understanding materials and materials preservation and trying, I guess, to beat Mother Nature in terms of taking these materials back via corrosion. So it's been a bit of a labor of love, and it continues to be.
Right. So our topic of the day is additive manufacturing, which is also 3D printing in layman's term. So generally what comes to mind is plastics, but there are a variety of other materials that can be used in this process. Could you give a few examples for us?
I certainly can, and I'm glad you mentioned that. So in layman's terms, it is known as 3D printing, which sounds exciting because it really is exciting. Additive manufacturing captures a whole range of other technologies which don't immediately, strike as a printing technology, but they are additive. But in terms of what materials you can use, that's a really, really, really good question. So the good news is nowadays you can additively manufacture all the major classes of materials, which is polymers, ceramics, and metals. So those are the three major classes of materials. There is a few quirks, and I think it's worth elaborating on what those quirks are. So one of the materials that you couldn't print until very recently, which is a subset of ceramics, was glass. And in the last year or so, the technology to 3D print glass has also evolved. There's a couple of companies that are doing that around the world. One is Micron 3DP, the other one is Maple Glass Printing. And in terms of I'll be totally honest. In terms of these classes of materials, you can print the majority of materials within these classes, with some exceptions. So there are some trade-offs in terms of additive manufacturing, and that relates to limitations from the technology used in additive manufacturing. So an example for metals, which I know is something that corrosionists get excited about, is that you can 3D print a heck of a lot more materials than you can actually make by conventional methods, but there's some that you can't. So you can't 3D print very reactive materials like magnesium or sodium or calcium, which are metals, because the way in which you're doing the additive manufacturing would make them explosive, or it could be dangerous. And similarly, things like arsenic that create a bit of a vapor. So I guess what I'd like to do, if there's an opportunity, to elaborate a little bit on how additive manufacturing of metals is done. And then you'll understand why some things can't be additively manufactured, but some other things that you couldn't access before actually can be. And that's where the excitement really lies.
Absolutely. Definitely.
All right. So I'll jump into a little bit of an overview of how the process works with metals. And this is going to really test my linguistics, because over a podcast, there's not any visual aids, but you'll have to all use your imagination, and so that's okay. I think you've all got a really good imagination, especially if you're already on this podcast. But look, for 3D printing of metals, there's two major technologies which make up probably about 90% of the usage at the moment. The first of those is called selective laser melting, where you have a bed of powder. So basically, you could think of it as a box of metallic powder, and then the floor of that box can move up and down. So what actually happens is a laser hits the powder bed at the interface of the powder and the environment, and when you've got the base of that powder bed up really high, you're able to print a layer, and then you drop the powder bed, and then you print another layer and another layer. So actually, 3D printing from selective laser melting is kind of like inkjet printing at home with your printer. It's a layer by layer process where each layer is added to the next one, and the melting of that powder locally is done by a very, very, very powerful laser. So that's that technology. And so in that particular case, it's not a free-form robotic arm that's moving around and building your part. That is the other technology, which is called direct energy deposition. And that's the other 3D printing technology that's very popular, where you basically have a nozzle that has a very large laser beam coming out of that nozzle, and a stream of metallic powder is blown into the path of that nozzle, and it's melted in the air or in the inert environment just above the substrate that it's going to hit, and then you build up by a free-form robotic arm. So those are the two key technologies. Both of them work by having a very high-powered laser, and so they make up about 90% of the market. But there are other ways of doing additive manufacturing. So if you pause about and thinking about 3D printing for the moment, and just think about how do we have a process that's additive as opposed to subtractive, where you're taking away material, you can also achieve additive manufacturing by what's known as wire additive arc melting, which is a little bit like welding, to be quite honest. So if you think about welding, if you're welding clumps on top of one another, you can generate a shape with very little material wastage. So wire arc is another process. Another process is electron beam melting, which is much like selective laser melting I spoke about before, but the local heating source is a focused beam of electrons. And then the final one is cold spray. So at supersonic speeds, firing powder without any laser into a substrate means that they collide onto one another and actually bond. The challenge there is that the speed of the powder needs to be blown at a very, very, very high speed. So we're talking, supersonic, so faster than the speed of sound. But there are commercial systems for all of those. So in total, I've mentioned 6 unique processes, but certainly the main 2 are the laser-based methods, and they're the ones that are gaining traction, not just worldwide in terms of R&D, but actually components that are now in a whole range of applications. So examples include custom titanium implants in humans for hip cups or femurs. Other examples include about 30 different parts for aircraft engines that General Electric is now using, and there's a heck of a lot of press all around these. And in fact, General Electric bought one of the main companies that produce these selective laser melting machines recently. So they are a producer of not just components, but a producer of printers to make components as well. So certainly a dynamic time in the additive manufacturing field.
So as you mentioned these 6 different types, what are some of the benefits, and why are we using a variety of techniques? Are some better tailored for certain processes, or for example, component shapes or structure or integrity, or?
Yeah, look, I mean, that's a really, really, really good question. In a way, the selection of technique is largely going to be informed by what the end use is, and that's a really nice point about additive manufacturing, because you can make niche components or bespoke components in small production runs with relative efficiency. what it means is you get to think about the whole of the process. And so you get to choose the method that you want to use for your production that matches the end process. So a good example of what might dictate a process selection is something like the final part size. So selective laser melting has one advantage and one disadvantage. The advantage is it has exceptionally good dimensional control. So you can build things with literally micron-sized resolution in terms of contours. You can 3D print directly, bolt heads and threads and so forth. But you're limited to the size of your powder bed, and so your powder bed, it can't be very, very, very large just for practical reasons. Whereas the other process, like direct energy deposition, the blown powder method, can actually make components that are, many, many feet, many tens of feet in size in each dimension at the loss of extreme dimensional accuracy. So there's some pluses and minuses to each of these. But in terms of what the benefits are more generally for additive manufacturing, I can deep dive into that a little bit because I think that's core to what we're talking about today. And some of the unique benefits, of course, that are really just obvious is the fact that you can produce things in net shape. So you can produce things in their final shape. And that means no wastage. So that's why the process is additive. Traditionally, what you'd have when you have wrought materials or even castings is you have finishing operations that remove material and your product is not in its final net shape. By being able to produce things in net shape, what it also means is that you can also build in part complexity. You can build in design freedom that comes for free. And you can also do activities that you couldn't do in the past. And this might sound a little bit sci-fi, but of course, we all probably have thought about if you had a 3D printer on the moon, you could build things on the moon and you wouldn't need, a whole factory there. And so that reality, toned down a little bit, is you could potentially have a 3D printer on board a ship. You could have a 3D printer in a remote community. You could have one in a hospital, where if something breaks down or if you need a mission critical component, you don't have to wait months and months for it to come from a foundry, in Seattle. If you're all the way in Melbourne, Australia, you can produce things locally. So it's decentralizing manufacturing in a very, very, very positive way.
Right, and then all you would just need is the metal powders or whatever components you have to go into it to make it, right? So you would have that on hand versus needing
Correct.
to
Yeah,
order.
that's a really good point. So you'd have that in stock, just like you'd have it in your pantry, ready to go.
Mm-hmm.
Yeah. So that is a good point. Yeah.
On most of the components, are you just using a single metal? Are you blending together different powders then to make that end product that you want?
Good question, Sammy. So generally, you can do both, and it depends what it is that you want to make. And so this is somewhere where I can babble on for ages when it comes to the alloy design and the alloy considerations. The key thing is the different technologies give you different flexibility in being able to alloy on the fly. So powder bed method, like selective laser melting, means that the composition of your powder bed is usually fixed before you start printing, but you can blend powders in there and generate unique alloys. And that's in fact what a lot of researchers are doing at the moment. So creating either unique alloys or mixing powders that have not been mixed before. Whereas direct energy deposition, because you're blowing powder into a stream, you can be blowing in from multiple hoppers and you get the ability to produce composite materials or hybrid materials or mixing metals and non-metals at the same time. So having ceramic metal composites, for example, using waste material in your feedstock. So it is a good question. You do have that metallurgical freedom, but your question reminded me of the one important thing that I wanted to mention here. When I mentioned earlier, you have some limitations with laser-based methods, like you can't 3D print explosive materials because the interaction with the laser gets to a very high temperature and things will go, pow. What you can do, however, is for materials that are not so reactive, which includes the transition metals, which includes the huge chunk of materials in the middle of the periodic table. So we're talking about dozens of metallic elements in the middle of the periodic table, can now be alloyed with one another. And that's part of the really, really, really big excitement about additive manufacturing of metals, where in a way those in the industry are now calling it a bit of a renaissance in metallurgy, because we have great opportunities to create a vast number of alloys that we couldn't access before. And for those that don't know much about alloy production and how alloys are made, whether it's stainless steel or aluminium alloys, normally there's a process where you go from a liquid and you cast into some sort of ingot at some stage, where you go from a liquid to a solid. And that's usually governed by mutual solubility of one element in the other. So it's kind of a bit like the oil in water issue. You can't make alloys where you get phase separation, where you have a separation of oil and water. You need to work within mutual solubility of materials. Now, in the case of mixing materials under a very, very high-powered laser, you have such intense power going into that local region that everything is annihilated quickly, and then it's rapidly solidified when the laser moves position to go and print, another bit of your component, that you get rapid heating and rapid cooling, that you're basically cheating nature in a way and able to create alloys that have never been seen before. So this is really, really exciting. I can't understate that. And with that level of excitement, of course, comes some challenges. And one of them is that what do you make now that you can create billions and billions of different compositions? And so people will be working in this area for a very long time, but for very good reason, I think, Sammy.
Mm-hmm. Right. That is exciting to be able to create new materials, blend new items together. What type of impact does that have on the actual properties, though? If you can blend new alloys and, let's say, have this whole new renaissance going, are you expecting? Can y'all predict what the structure is going to be, how it will hold up, how it will last long term, or the corrosion properties, anything like that?
Yeah, look, these are all really, really good questions, which are
a little too early to know?
Well, look, in a way it is, but these are the important questions to be asking right now, and these are the important questions to be putting forth to the corrosion community, because we have the opportunity to learn lessons from the past where normal alloy development, took upwards of decades, many decades put together, if working in isolation. So now with better communication, with better characterization, we have the ability as a community to move the dial quicker. But look, when you mentioned, I'll try and keep it high level, but when you mentioned what type of impact can the process have on the properties, inherent to 3D printing, and it's regardless of all the methods that I mentioned earlier, to some extent you get rapid solidification, and you get that to a large extent with laser-based processes. So what it means is you're developing structures that are basically frozen in time in what may be a so-called metastable state. So how their long-term stability plays out is something that's yet to be seen. And I mean, in cases for the very, very long term. I don't mean days or weeks, I mean in the very, very long term. But it also means that we can start to ask fundamental questions. So like I alluded to earlier, metals, which is largely what we make structural materials and engineered components with, in their own right, they're already a human-made endeavor. So, you don't just walk around the forest and find big chunks of metal. Usually they're refined from ores and minerals and have a lot of energy put into them. So metals themselves are a human-made construct that are largely metastable regardless. And so it gives us a philosophical way of a new philosophical lens in the way we design materials. The good news is, though, Sammy, is that the properties so far have been considered to be quite excellent for 3D printed components. And I'll say that with a little star next to it. When I mean excellent, I mean the rapid solidification usually means that you get fine grain structures, and that you get good chemical homogeneity through these through components. So there are some real benefits, and that translates to higher strength. But if process control starts to become an issue, then you may have defects in there, which deteriorate properties as well. And I might just elaborate a little bit further on some of the challenges when studying additively manufactured materials, because process is a big part of that. So if it's okay, Sammy, I'll elaborate a little bit on some of the challenges.
Absolutely.
Yeah. So look, one of the things when you're 3D printing metals, and if you Google this, or if you look at some of the research papers, is there's a few key challenges that are evident. One is the reproducibility from different instruments, in different countries or different states or different continents. So the reproducibility of properties from instrument to instrument. And so what that means is, a researcher or a factory in one country may use a certain laser power. And in another factory, they may use a different laser power. Both of them make a solid material that looks the same, feels the same, and has the same application, but has different properties. So fortunately, in the last couple of years, the not-for-profit entity in the US called ASTM has looked at implementing standardization processes across additive manufacturing, which is of course really, really useful. So reproducibility remains a challenge, but of course the other challenge, and this is where finally we get to talk a little bit about corrosion, is defects and defect control. So what would be considered a satisfactory build of an additively manufactured component is if you can build it with the minimum amount of defects towards negligible amount of defects. And so I'm talking about inclusions, oxides that might come from interactions with gas or pore environment control, or even porosity. And there's various types of porosity. So minimizing those is important for defect control. But if you can't minimize those, where the challenges are is what effect is that having on corrosion, and do we understand that effect? And I think it's probably fair to fall on our sword as corrosion engineers and say we don't understand completely at the moment the effects on corrosion of defects that can occur in additively manufactured materials. And so to pick one example, if you have a material that's printed and not 100% dense, it could be 99.5% dense and have some porosity throughout that material. What will that do to its long-term corrosion behavior? Now, research to date has indicated that it actually has perhaps fortunately, minimal to negligible effect on corrosion initiation. But what research is also showing is once corrosion has initiated, it's much more difficult to repassivate such materials. And getting to that level of understanding for our field will be important before 3D printed components ultimately go for vast, sort of mass market type applications in the as printed condition. I should say there's a lot of clever people out there that have thought about this, of course, and there are ways of avoiding. I wouldn't say avoiding, correcting defects in 3D printed components after you have produced them. So there are various heat treatments, or of course hot isostatic pressing, which is what can be used to provide a heat treatment and pressure into a component after you've built it, such that you minimize or eliminate the porosity. And of course, that's typically what's done to components that are going to end up flying, or ultra-critical components that are going to be subject to repetitive fatigue loading and so forth. But of course, the holy grail would be to be able to have a printer somewhere tell it what you need, it makes it, and then you take it out and then you use it. We're not there just yet for a lot of engineered components, but we are for a good number of them.
That's promising, and it sounds like there's a lot of areas for future research to kind of continue in the field, both in terms of building the alloys, in terms of how they last, corrosion properties, things like that. We're getting near to the end of our time. Do you have any additional things you'd like to say before we wrap up?
Yeah, look, Sammy, I think this is a really hot topic, and I'm delighted to have been the one to be able to talk about it. But clearly, there's a lot of great researchers, both corporate and academic, that are working on this at the moment. And so I'd encourage the field to communicate and talk to one another, and really share experiences, share knowledge, because I don't want to overstate it, but materials really are getting critically important in the next 10, 20, and sort of 50 years. So if we think about some of the grand challenges that we have facing, our societies, things like clean energy, clean water, things like cheap air travel, all of these, aspects, or personalized medicine, all of these aspects can have a step change in their deployment through additively manufactured metals. And so it really is that serious. And so I'd encourage people to keep an open dialogue with one another and engage with one another, and certainly engage with those involved in NACE. And I'd be delighted to connect with as many listeners as possible on this topic.
Thanks, Nick. And on that note, what's the best place for them to go if they want to learn more about the research you're doing or if they want to connect with you?
Yeah, look, I'm very responsive to email, so it's nickbobellis@anu.edu.au. You can find me pretty easily because I think accompanying this podcast, it will have my name. So if you pop that in a web browser, you'll be able to find me through your favourite social media platform. And of course, I think it would be only fitting to continue the dialogue through NACE as well and their various platforms, because this is really, really a hot topic and exciting, and I can't wait to be able to collect and share more results on this topic, as I know other researchers in this field are also itching to do.
Thanks again, Nick. And on that topic, for listeners who want to learn more about corrosion of additively manufactured metals and alloys, Nick was actually one of the co-authors of a review article we published in Corrosion Journal in December 2018. You can find that on our website at corrosionjournal.org, along with a number of other articles that we have on that topic, more recent than that. With that, I'm Sammy Miles, and thank you for listening to the first episode of Corrosion Journal's interview series. If you want to learn more about the journal, make sure to visit corrosionjournal.org. You can also subscribe to NACE podcasts if you haven't already on Apple, Google, Spotify, and all the major distributors. And you can also find all of the episodes of NACE podcasts on nace.org, which is nace.org. We'll be back soon with another episode of Corrosion Journal's interview series right here at NACE.